Okay, so now I want to work this one. It says the diagram above illustrates a velocity selector labeled region 1. It consists of two parallel conducting plates with charges on the plates as indicated, creating an electric field of magnitude E directed toward the top of the page because fields go away from positives and toward negatives. A uniform magnetic field of magnitude V1 directed out of the page exists between the plates. The magnitude of the magnetic field can be adjusted so that only particles of a particular speed pass through the selector in a straight line. A radioactive source to the left of the selector emits charged particles, each having the same charge plus Q, moving to the right into the plane of the page. The effect of gravity can be neglected throughout the problem. Okay, so they want me to give them an equation for part A, derive an equation that shows that V is equal to E over V1. Okay, so what I said was, all right, that's not too tough. I know that E is equal to F over Q, because that's just electric fields. And I also know that the force of an electric field can be rearranged by writing that equation differently, E times Q, and that if my particles are going to go straight through, then I can set those forces of the electric field and the magnetic field equal to each other. Okay. All right, so let's see if we're good to go so far. So if I set F, force of the electric field, equal to the magnetic field force, I have EQ equals BQV. Those are going to cancel. So the velocity is going to be E divided by V1. So there's the part 1 that they wanted. Part 2 says some particles are emitted from the source with speeds greater than E is E divided by V1. Which of the following describes the initial path of the particles immediately after entering region 1? Well, we know that the speed is greater than this quantity right here. So if it's greater than this quantity right here, it tells us that this is held constant, but this we can mess with. So obviously something has happened to the magnetic field. They've changed it somehow. Okay? And we know that if the the speed increases, the field must be increasing. Okay, is everybody all right with that? And let me keep going on. All right, then, if that's true, then I need to use the right-hand rule. And when I used the right-hand rule, I said, well, if the force of the magnetic field is greater than Fe, then the particle has to be pushed that way because the electric field is the force of the electric field is in that direction. So the force of the magnetic field must be this little rascal right here. So it's going to curve down like that. Okay? So it curves toward the bottom of the page. And then I have to explain my reasoning. So I just said all of that, but now I'm going to explain it. The FB is greater than the electric field force. So particle will move in direction of the magnetic force, which is down the page. That force is perpendicular to the velocity. So FB is supplying a centripetal force, causing it to go in a circle. Let's go back up here and make sure you understand this. If this charge is positive, then this plate is going to repel it, so the electric field is going to shove it in that direction, or want to. All right? Now, as long as they're balanced, it moves straight through, but as soon as this value gets greater, it's going to force it toward the positive plate. It tells you in the problem that this field is constant, but you can manipulate the magnetic field. The electric field is constant, but you can manipulate the magnetic field. All right, so we've got part A, 1 and 2 done, and that's a lot of work. Now let's move on down to this next one. All right. here it says, a constant magnetic field of magnitude V2 is directed into the page, added over here in region 2 to the right, as represented in the figure below. Suppose a particle leaves the radioactive source, travels through region 1 in a straight line, and enters region 2. For each of the following, express algebraic answers in terms of V, V1, V2, Q, and fundamental constants as appropriate. All right, so then I said, okay, part B wants me to determine an expression for the initial magnetic force on the particle in region 2 and state its direction. So I said, well, the initial force is going to be V2, because it's in field 2, QV, but I need the speed that it left with. So it left this field with the speed of V is equal to E over V1. We already got that in part A. So now my initial magnetic force is going to be VQ E over V1, and this will be V2. Or you could just say V2 E Q all over V1. So that makes sense. Now I need to talk about the direction of it, so I'm going to use my right-hand rule. And let's see if I can get that going. Okay, this time the field is in the direction opposite of what it was in region 1, and in region 1 we said the magnetic force was that way. So if we're in region 2, that's the direction of the magnetic force because of region 2. You can also use your right-hand rule. It's a positively charged particle. The field is into the plane of the page, so your palm would face to the top of the page, which is your force. All right, then it says, part C says, describe the changes, if any, in the magnitude and direction of the magnetic force as the particle moves in region 2. So force caused by field 2 is going to be opposite in direction. Compared to what it was in field 1. And then I said there's no E field. Does not exist in region 2. So I don't want to say so. I want to say and. E is constant, so the force of the magnetic field is constant. Okay, got interrupted, not real sure where I am, but we're going to figure it out. Okay, so I said it was V2 is opposite, that force was opposite because the field was opposite. I had no electric field there. And I said that region 2 had a constant magnetic field. And then I did use the right-hand rule and showed particle moves
Sarah Darling, please call extension
in a circular
2001.
path.
Sarah Darling, please call extension 2001.
Directed toward the top of the page. And so I think I might have answered part D at the same time I answered part C. You could draw a picture if you wanted. Moving something like that, because there's the force directed inward. Okay, and then E said develop an expression for the charge-to-mass ratio, Q over M of the particle. Specifically note any quantities not previously defined that are included in your answer. So I said, okay, well, let me look at part E. Well, I said now it was over here, so centripetal force was created by the magnetic force. And I said, well, if that's true, then mv squared over r is equal to bqv. And I said, well, I know v is equal to e over b1. So I kind of went ahead and reduced it down. So then I was left with m over q is equal to b r over v. but that's not what they wanted. They wanted Q over M this welfare, so I got to go back and fix that. So I should have said Q over M is equal to B over, all right, so I have B over RB. All right, and I substituted E over B1 divided by R over B2 is equal to Q over M. Okay, well, everything was looking really good. And then when I rewrote that, that gave me Q over M is equal to the electric field over B1, B2, R. And I'm going to put a capital R here because I want them to know that that's the radius of circular path 2. In region 2. And that was where it said specifically noted in quantities not previously defined that are included in your answer. So that's what they're talking about there. All right, and I think I'm done there. Okay.